what I want to talk about, why I want to talk about the physics of the blues. What I'd like to do is kind of a very eclectic presentation where I'll take you through the origin of harmony and scales in Western music in the last 300, 400, 500 years, ending up with the blues at the end of my talk. And what I'm trying to do here is a couple of things. One of them is to show you, if you don't know this, that there's a lot of physics and mathematics in music, which is intrinsic. Even those who aren't mathematicians who know and appreciate music probably are using this somehow in their brain. And that, to me, is fascinating. And the other one is to try and forge a connection between art and science, which I think are much more intimately related than sometimes people realize. So let me start with that point. If you look at these pictures on the right here, this is an example where science and technology drives art and design. So I used to live in Chicago, and as you probably know, Frank Lloyd Wright was an architect from Chicago, the turn of the 20th century, who was very highly regarded around the world. Beautiful buildings, many of them in that part of the country. And he was struggling with a lot of technological challenges, one of which was windows. He wanted big, massive light spaces, but he couldn't do it with the technology available for glass and structural support. He also struggled with chimneys, by the way, if you're interested in that aspect. So now look at what we can do today thanks to technology. You have these all-glass buildings, which I'm sure if Frank Lloyd Wright had been around, he would have been able to use in some way. At the same time, the technological limitations led to a form of art and design which itself is beautiful and creative and fascinating. One of the things I think you see when you look at science and music is the constraints that are available from instruments, from the physics and mathematics, actually drive creativity on the part of composers. And there's a very intimate link there. This is a painting I particularly like of a steam engine from Turner back 100 years earlier, showing the sort of beauty of technology. But I often point out, especially to non-scientists, many people who aren't scientists don't know anything about calculus, and they don't need to learn calculus, but they miss out on the fact that calculus is an amazing mathematical language. So this little equation, whether you understand it or not, the Laplace's equation, which has, as you can see, 5 symbols, basically contains all the information needed to understand how to design the wing of an aircraft in terms of the flow of air, or can explain to you how lightning propagates through the atmosphere and a lot of other things. Can you think of a sentence with 5 letters in it that could possibly contain that much complexity? That's beautiful. I mean, that is beauty. It isn't just about rigor and so forth. So there's an other side where I think people who are outside science don't realize that scientists and engineers are driven by elegance and beauty. They want an explanation that's simple, and if they have 2 explanations, one is 50 pages and one is half a page, they're going to like the half-page one much better because it's somehow closer to the truth. So that's beauty and creativity that drives science and engineering as well. It's a two-way thing. And of course, you could talk about, it used to be said, the left and the right side of the brain, but I think that's not correct anymore, but the concept of parts of the brain that are analytical and parts of the brain that are more creative, and how they're linked intimately together is a very interesting aspect of this. So let me talk about sound. So sound is a pressure wave. When I speak to you from the loudspeakers of my voice, there's a wave of pressure that is hitting your ear, and that's how you hear the sound. A critical thing that you need to know is that the pitch of a note, like A here, is a frequency. The difference between A and E, your ear is measuring the frequency and converting it into a pitch in your brain. And so something I like to point out to people who aren't mathematicians or physicists is that waves, sound is a wave. Waves are a very, very fundamental thing in science. They come up over and over again. And the reason they do is they have a very simple symmetry. They look the same in space, if you take a snapshot, as they do in time if you stand in a place and watch what happens. So for example, with my ear here, if you look, you take a picture of the sound, you can see the pressure waves. There's a periodicity to these with a spacing between the peaks, which is called wavelength. If instead of doing that, I stand in the ear and count with time how the pressure changes, it looks identical. And it's actually that property, the symmetry of space and time, that makes waves so important, interesting, and relevant to our lives. So the time it takes between the peaks of the wave is what's called the inverse of the frequency. So a 440 hertz concert A means 1 over 440 seconds is the time between the peaks of that wave. So clearly your brain is measuring frequency when it hears pitch. The second thing you need to know is that when you cause an oscillation in a physical system, you typically get harmonics. So you won't get a pure pitch. In fact, there's a set of layered sounds on top of the 440 hertz. 440 hertz is another way of saying the frequency. And those are typically integer multiples, so it's twice, 3, 4, 5. This picture here is taken from a stroboscopic image of a string vibrating. So anyone who plays a guitar knows that if you pluck a string and then place your finger in the middle, you can damp out the first fundamental, but you then hear twice the frequency, which is the oscillation which has a node in the middle. There's also 3, 4, and 5, and good guitarists can actually express those by damping at the right point in the string. This is very important because it turns out that these harmonics are integral to most vibrating systems. It's basically simple physics. If it vibrates well, it will typically not vibrate in a simple fundamental way that have these harmonics. And the ratio of these harmonics determines the quality, or what musicians would call the timbre of the sound. So to give you one very simple example, this is a whole lecture in itself, but the difference between a piano and an organ has to do with the fact that only in an organ, because of the shape of pipes, one end is open, the other is closed, only odd harmonics are present. 1, 3, 5, 7. With a piano, guitar, trumpet, they're even and odd. And that gives one aspect of why organs sound distinctly different from pianos and so forth. In fact, there's a thing called Fourier analysis in engineering. This is actually a very interesting way to introduce Fourier analysis to people because it's just a harmonic analysis. You can express any complicated system as a set of frequencies. And this way of looking at it is called Fourier analysis. So when you try to understand musical sound, this harmonic analysis is very useful. But the reason I want to bring it up now is when you try to understand harmony, so we're going to talk about scales and music, when two notes are played at the same time, if they have overlapping harmonics, they're going to sound consonant to your ear. For those who don't know music, the notes on the piano, C, D, E, F, G, A, B, are labeled that way. And on the scale, they would look like, on the musical scale, they would look like this. There's a funny notation that's used in music for intervals. Interval basically means playing two notes at the same time or near each other. So this interval, for example, C and E, is called the third. This interval, C and F, is called the fourth. This interval, C and G, is called the fifth. Why is C and C is called the first? And this has got to do with the fact that the Romans didn't know about zero, the Greeks did. So they didn't know how to say zero, so they said one. So it always confused. The second is the smallest actual interval that you can get. So we're going to talk about what these intervals, when you play two notes together, your ear will hear if there's some relationship in the frequencies of the harmonics, and that's what determines where harmony comes from. So we're going to build a musical scale based on these harmonics. And I first want to start with the idea that a scale is like a palette. And we'll talk a lot about scales. The scale is a palette for a composer on which to compose. And there's some fundamental physical and mathematical issues that determine the properties of scales, which must therefore be revealed in the composition. So I'm going to try and expose those and show how they've evolved. So I pointed out that a single string like C, a single note, will have all these harmonics. And on the piano keyboard, their positions are C, the second one, which is twice the frequency, is the next C, then G, then C, then E, then G, and then something near B flat here, and then C again. So it's this set of notes here. Those are all the harmonics that are coming when I play just that one note C. They're all in there. You don't hear them explicitly, but they're in there, and you will hear them when you hear relationships in music. So the first harmonic is twice the frequency, C and higher C, and that is the octave. That sounds very sensible, as opposed to the octave. You can understand why it's a favorable interval, because it's twice the frequency, and the overlap is such that this note overlaps with the first harmonic of that note, and that gives you the sense of consonance. The next one is a G, up here. You can bring that G down one octave by dividing by 2. So then you get this note, C and G. So imagine I'm constructing a scale. Pythagoras was the first to do this, at least that we know about, from scratch, starting with just one note, which is your C. The first sensible one after the octave that you come to is this G. And this G is known as this interval, C and G, is known as a perfect fifth. It's called perfect because it has very, very strong resonance. The first harmonic of this G is the same as the second harmonic of C, and you can hear that, as opposed to nearby intervals, like assuming here that that fifth is a very harmonic interval, and it's the basis of the beginning of the construction of a scale. So now you have two notes, C and G. Your next step would be, by the way, I put a point here for those who are interested in the mathematics or physics. The piano keyboard is basically a slide rule, because you'll notice that every time you go up an octave, you double. So if you add things on the keyboard, it's equivalent to multiplying. And it turns out later you'll see the logarithmic nature of frequencies is really a critical part of the tuning of a piano. So I mentioned unison, octave, and the perfect fifth. If you continue to do this, so I'll basically take C and G, G and D, B and A and E. I now have 5 notes. I bring them all back into the first octave, and those notes are the very famous pentatonic scale. In almost every civilization, the scale has emerged. It's such that if you play any of these together, they're all in very nice ratios. They sound okay. They sound very harmonic. So a pentatonic scale is... Now, once one combination you play them, and they can sound okay together. If you're interested, the black notes on the piano, for reasons that are rather sophisticated but interesting, are in fact the pentatonic scale in the key of G flat. So if you just play the black notes, you have a pentatonic scale. To give you an example of how common this is culturally, music like this sounds sort of either Chinese or maybe Native American. On the other hand, this is very clearly Scottish. That's all done with black notes. Therefore, it's a pentatonic scale. So the pentatonic scale was the first scale to emerge, and music was then created on that scale. If you're also interested, by the way, if any of you are Marx Brothers fans, not many people left, then Harpo plays the piano with his elbows, and he uses the black notes. So that's why you get away with that, in a sense, right? So I encourage you to learn to play the piano with your elbow. And the pentatonic scale is very strongly used in jazz. One thing about jazz is it's a very harmonic kind of music. It brought back some simple harmonies that were always there, but had been forgotten by sophisticated Western musicians in the 18th and 19th century, and brought them in very firmly. Okay, keep going, and doing the same fifths, you can create the so-called diatonic scale, D, D, E, F, A, B. So, do, re, mi, fa, sol, la, ti, do. That's the classic scale, at least in Western civilization, that we all know. You could go, what I'll show you later is, if you continue to do fifth, you'll never come back to where you started from. You'll actually never end. You'll have a scale with an infinite number of notes. And the reason, remember, every time you do a fifth, you're multiplying a frequency by 3 over 2, and then dividing by 2 or multiplying by 2. So you're ending with 3 to the power of something, and 2 to the power of something else, and that can never be the same number, because one is even and the other is odd. So this is immediately the first paradox based on mathematics of scales. You can never make a self-consistent scale. You would go on forever and you never get back to the note you started with. What's interesting is when you go to the 7 notes, you come real close, within about 1%. The next match comes at about 35 notes. So you can see why people stopped at about 7, because a scale of 35 notes in one octave is difficult to play and complicated and so on. So all of these notes have a low ratio, integer ratio, and therefore they sound harmonic, which is the basis of the diatonic scale. Now, I mentioned thirds before. Let me just emphasize 2 kinds of ratios. The major third, which is C and E, has 1, 2, 3, 4 steps. They're called half steps or semitones. Whereas the minor third, such as D and F, has 1, 2, 3 steps. And therefore the ratios are different. And it sounds different, major, minor. They're both harmonic, but they have a different characteristic to them which you recognize in music. So now let's think about creating triads. So the first step in making harmony was to create 3 notes together. Nowadays in jazz you need at least 4, probably 5, to make an interesting jazz chord. But in the old days, back in the days 500 years ago, 3 notes was a sophisticated harmony. And so you take C, E, and G, and make the major triad of C. So you build that little set of basically 2 white notes, stepping up two white notes, on every note of the diatonic scale, and you'll notice something interesting. There are three different kinds of ratios. The one on C, the one on F, and the one on G are major. They have the same characteristic, we call them major. They're the same sound characteristic. The one on D, E, and A are all the same ratio, and it's minor. Finally, there's one odd one on B, which is called diminished, and it's kind of weird sounding. It doesn't sound very harmonic. So right away you can see these three chords, as they're called, C, F, and G, are the basis of creating some sort of music. So you can find these books, How to Play the Piano in an Hour, which teach you these three chords. The guitar, the same story. Play C, G, well, the key of G, say G, D, and C. You've got all the chords you need to do folk music. So for example, for my day, or a little bit before my day, but there's an infinite amount of music of that kind. In fact, basic rock and roll is on those three chords. So you can sort of see why they share a common sound that we sort of enjoy. We recognize it, and it creates a structure on which to imagine composing and so forth. This is actually a list of all the ratios, if you're interested, for the 12 notes on the first scale of the piano in this so-called just tuning effect that I talked about. So there's the 3/2 for the G, the 5/4 for the E, which are the lowest ones, and so on. So what's wrong with this? Apart from the fact that it doesn't complete, this is a nice scale to work with, isn't it? Why don't we just stick with this? Well, let me go back to Baroque times and play you some Baroque music. So we're going to take the canon in D by Pachelbel, very famous. And I'm going to tune, now this is the great thing about modern electronics, I can touch a button and tune this instrument in the way I just described. That's not the way it's been tuned, what I played so far. Well, I'll show you the difference. I'm going to tune it in the just scale of D and play you, as written there, the canon in D in that scale. Sequence of triads that are based on the diatonic scale, in this case the key of D. You can start with any note and create a diatonic scale. I showed you C before, now I'm in D just to make it complicated. So what's wrong with that? Well, I'm playing this music and Dagmar over here wants to sing along with me, but she sings a little higher. So I decide to raise it up to E flat, one semitone higher. Tuned in the way it would have been. It's out of tune. Not surprising, because when you think about what I said, if you were to start with another note and develop all these ratios, they wouldn't be the same notes as the ones you worked out for the key that you've originally tuned in. They're all different. So there's a fundamental problem that you've got, every key has to be tuned independently. So if you were performing with lots of people like Dagmar and others, you have to have the 12 pianos ready to transpose. You couldn't just transpose the music, you have to get a newly tuned piano. Well, that's one problem. But there's really a bigger problem here, and that's creativity. So you go beyond, you come now to Bach, who actually would like to introduce complexity into the music beyond just the chords I showed you, and actually bring the chords from other keys in when he's playing in C or D or whatever. And this is musical, this is the palette. He wants a bigger palette, where he can bring an E-flat chord into a piece in D to create complexity and interest. Can't do it with this tuning. Impossible. So he drove for a compromise tuning now called equal temperament. There's a long history of the evolution of this scale. And that basically is a compromise where every key is out of tune by about the same amount, and they're sort of okay. So we get used to it and it works, but it allows us to transpose and modulate between keys in one piece of music. So to show you, going from the old tuning, which is fine in D, but bad in E flat, or any other key you might want to pick, let me now go to equal temperament. which I do with a button, and play in D. Let me shift it up to E flat. It's okay. They're equally in tune. And you get used to that. So what is this mysterious scale? It's very, very simple for a mathematician to understand. It's a logarithmic scale, where every note is evenly spaced on a logarithmic scale. And the ratio between notes, because remember, a logarithmic scale, when you space it out, is equivalent to multiplying. So every step is a multiplication step. That multiplication is 2 to the power of 1/12. So if I do 2 to the power of 1/12, 12 times, I come to 2, which is your octave. And so every ratio is identical, and any interval will be the same ratio, no matter whether it's starting with an E flat, or with a B flat, or with a C, because the ratios of those notes are all identical. And what you hear is related to the ratio because of harmonic overlap. So this kind of solved the problem of creating a piano that was in tune in many keys. Of course, it led to a lot of concern. In fact, it's very interesting to read about this. I'm not an expert in it. By the way, I should declare I'm an amateur here pretty much, taking a serious interest in this, but it's not my field of research. But I did go into reading a lot of some of this stuff, and there were people calling this the devil's tuning, you know, the fact that you broke the perfection of the fifth. The fifth is no longer a 3/2, so you'll notice here, it's off by 0.45 hertz. So it's about 0.5% or so low. And you can hear that. That's how piano tuners tune the piano. They can actually tune. I often point this out to people. A piano tuner knows all this stuff and actually mistunes deliberately. So they'll tune the interval correctly, and then they will lower it until they hear the beats, which is a difference frequency. 0.45 hertz is 2 hertz. A cycle every 2 seconds. So if I was doing the tuning, I would start with wah, and then I would start to hear wah, wah. If I go too far, wah, 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 wah. I can do that with incredible precision. That's called the Vernier Effect. If you're an engineer, you know about this. It's a way of getting incredible precision from old-fashioned techniques. So it's done by piano tuners today. They do a lot of other fancy things as well, but basically it's all, they get this scale by a process of actually mistuning intervals. So what is so good about this? It allows now the introduction not just of playing the same music in different keys, but here is really the breakout of this, at that time, the romantic musicians like after Bach with Mozart and Beethoven. I'm going to show you some example with Mozart, just one example. This is his sonata in A major, which starts like this. Excuse me. But I'm going to go to further in the piece in the trio where I can just show this very easily for you. In the key of D. So let me go back to the old tuning and try to play that piece. So where I just was at the end there, back in the key of D sounds fine. In fact, it's even nicer. But now let me go to the part where you'll notice, if you recognize music, he actually modulates. The word modulation implies you change keys without actually telling anyone you did it. Transposition is where you just shift the whole thing up, and that's just, But modulation is adding complexity into music. Sometimes there's even ambiguity. Bach will do this, and you don't even know he's done it. That's what makes the effect. So you don't want to know all this stuff. He just wants to be able to do it. And so if I play Mozart now in the old tuning, immediately it starts okay here where we're doing this passage. That's fine. He couldn't have written this richer, more complex music. So one of the things you'll sometimes hear musicians say is, it was a big disaster after we introduced equal temperament, but it really was a creatively driven. It was a compromise not driven by the desire to be simple, but to add complexity and richness and beauty to music. So that's the one important thing I'd like to emphasize. And again, it was driven by mathematicians and physicists who figured out how to go forward with this, in a sense, I mean, at least that aspect of the tuning of pianos, beginning with Pythagoras himself. So I'm going to talk about some other harmonies in music that are really easy to explain their origin from the things I've talked about. One of which is the so-called dominant seventh chord. If you play the guitar, you're used to the C7 or the G7 as one of the sort of classic chords. You probably would play in the key of G, you'd play G, C, and D7. Those are your three chords, not D. What is the seventh chord? Well, you add one more note. So remember, the triad has three notes on it, which would be C, E, and G. You add another note, which is this B flat. And you create a chord which sounds very harmonic. So we do that. There's the B flat. It's actually very harmonic. Oh, I'm still in the wrong tuning, excuse me. Didn't sound quite as harmonic as it should have. So this is very harmonic. And you can see why, because that note is in fact a high harmonic of C. On the earlier picture I showed you, this note, 3 octaves up, is one of the first harmonic you get, which is not C, E, or G, is a B flat. So your ear knows this is part of what you're hearing. But now you get this really interesting thing, because when you hear that, you want to hear something else. You hear a C7, you kind of think, something's coming, that. There's so many. Why is it that happens, that you see these C7s always being preceded by what's called a fourth? And the answer is that this note is not in the scale, at least I think the answer is. Remember, the diatonic scale has C, D, it doesn't have B flat. So you might say to yourself, well, you hear this beautiful harmony, but this note isn't right, it shouldn't be there. So where is this note? Well, take the first diatonic scale, which contains only a B flat and no other black note, and it's F. F has F, G, A, B flat, C, Do, Re, Mi, Fa, Sol, La, Ti, Do. So when you hear F, you feel good. You knew it was good, but it wasn't quite right because you had this funny note. Now suddenly you're resolved. And that's at least that's my explanation of what is called a cadence in music. And it's really based, again, on this very basic aspects of physics and mathematics that you always want to hear. And then, so if I go to the next slide, I actually show what's called the circle of fifths, which is the relationship between all these. If I start with C, go C7, then F. F7 takes me to B flat. B flat 7 takes me to E flat. E flat 7 takes me to A flat. A flat 7 takes me to D flat. I work my way around the keyboard playing all these keys, and you hear that, it doesn't sound ridiculous to you. It sounds okay. I'm jumping between keys, but the logic of the jump is one that you can recognize because it's harmonic aspect. So now you have a way of taking you in music easily from one key to another using the circle of fifths. And that was done extensively, still done today in music. So I'm going to show you a couple of examples of it. The first one is this, I like to think of warm places this time of year. B, F sharp minor, G. It's rich complexity harmonically, and the jump of a fifth is used to take you jumping through these remote keys in a way that you feel comfortable. It's not like a random, you're just jumping randomly in some key. You'd say, what's going on there? So it's a tool. It's another bit of a palette that you have as a musician, which requires, of course, equal temperament tuning. Otherwise, only one of these would be in tune. Only one of these keys would actually work. Another example comes from from Beethoven. I'm sorry, not Beethoven. From the Beatles. It starts with a B. Again, I bring up my age, although I have to admit my kids are a little older now than a few years older than many of these students, but they admitted they heard my music and they actually got to like it, but they'd never admit to anybody. So you guys may have heard some of this stuff. And so the Beatles, interesting because Paul McCartney was the composer in the Beatles. And he was musically trained. And so back at the time when rock and roll, of course they brought rock and roll, he and that, he actually added more complexity. Instead of just the C, F, and G that everyone was doing, he used more complex music, and something characteristic of his tunes anyway. So this one, for example. There. That was using a fifth to jump basically down here from E minor into A major, and he does it several times in this piece. So they had slightly more complex music, and they brought that a little bit into popular music back many years ago. Okay, a little bit more before we get to the blues. One more chord which is really interesting from a physical point of view is a diminished chord. I mentioned when you build those triads in the diatonic scale, one of them, which is on B, D, and F, has a weird sound. It's unlike the others, which sound pretty harmonic. It sounds a little bit dissonant. In fact, if I could do that on C, C major, C minor, C diminished. It's a very interesting chord. Why is it so interesting? And the answer is it's made up of two intervals, like all these triads. There's the first interval, 1 and 2, and then the second interval. And in the case of this chord, the two intervals are identical, and they're both what would be called minor thirds. So let me go to the example of C diminished. I would have the minor third, which is part of the minor triad. Add another minor third, which is equivalent to like the minor third in the key of E flat, if you're interested. And I get two harmonic intervals, both of which are nice. I put them together, and there's dissonance because this note, which is G flat, and this note, which is C, don't resonate strongly together. They're actually quite dissonant. So it's two intervals, each of which is fine, put on top of each other to create this interesting murky thing, which is both harmonic and also dissonant. That's one thing about the diminished interval, which is a diminished chord, which is interesting. But there's something else. What physicists would call degenerate. If I start with the key of C, I can build all of the triads, say on C, C major, C minor, C diminished. Let me go to D. D major, D minor, D diminished, so on. All of those are distinct except for one thing. The diminished chords are degenerate. The chord C diminished is the same as E flat diminished, which is the same as F sharp diminished, which is the same as A diminished, which is the same as C diminished. They're exactly the same chord, the same notes, just in different order. And so this is very interesting because it brings in the ability now to jump into very remote keys, because suddenly, by simply going to the diminished chord, you then got the possibility of going in several different places. And that is used extensively in music as well. And I'm going to give you a couple of examples of the diminished chord, mostly focusing on the sound of it. The first one is Chopin. So during the Romantic piano period, the diminished chord was heavily used, and is sort of associated somewhat with the Romantic music of Chopin. And you can hear this. I'll play one of his nocturnes. Has that candelabra, my midnight in a Paris salon sort of thing that Chopin is good at. Now let me give you Beethoven. So this is Beethoven's Moonlight Piano Sonata. And I'm not going to, the famous, of course, is the beginning. Instead, I'm going to go into the middle of it here, which is sort of starts on the board there. And you'll see it starts actually in the previous bar in C sharp minor. And that's a diminished chord being expanded. Minor again. Diminish. You sort of hear that unusual harmony of the diminished chord that's both harmonic with those intervals, but also creates a dissonance, which I think is a characteristic of it. I'm not trying to deconstruct music here. What I'm trying to emphasize is there is a lot in common, and your brain must be using some of this when you hear music, between the physics and mathematics that drives it and the ability to create on the structure that is thus created. So it's a palette, as I like to emphasize. So now I want to come to the blues. And this is just a very simple example of an artifact in the way piano blues is played, which has emerged from the scales I talked about. So you have to place yourself back in New Orleans in 1900, and you go into places in the bars and the brothels and other places where people like Jelly Roll Morton are playing the piano. Now these people, we're talking here about the influence of music that came from Africa. And one thing about African music is it's very sophisticated rhythmically. Actually, fascinatingly so, polyrhythmic in ways that we haven't explored as much in the Western. But it's simpler harmonically and melodically. And they were partly influenced also by being forced to sing hymns, which are extremely simple harmonies. Typically, those 3 chords will do with a lot of hymns like Amazing Grace, for example. So what you had is bringing together simple melodic and harmonic things, like I talked about in the old tuning, with with the existing scale. And what you find is there's several places on the scale where there are notes which are really missing. And the one that I'm drawing your attention to here is sometimes called the blue note. If I look in the key of C, this is actually what people call the blues scale in the key of C. But you'll notice that one of the notes is actually named as E flat. But this note is really not E flat. This note is between E flat and E. This note is actually the perfect major third, which is ratio 5/4. It's one of the very harmonic intervals. But in equal temperament, that note is far out. If you ever tune the piano, you'll actually find this is the difference is about 12 hertz. The beat frequency is quite high. And you hear that. It's one of the things that gives a characteristic to piano music. If you hear the thundering chords like in Beethoven's Emperor Concerto, which are basically these triads in C, there's something about that which comes from the major third which is not very harmonic. It's sort of bright sounding because of the fact that this interval is really out. Now the E flat would give you the minor. So here's your major, here's your minor. What you're seeking is a note between the two of them. So what happened was, because bringing, as I said, this African-American music in the form of the beginnings of the blues, playing on Western keyboards with equal temperament tuning, people like Jelly Roll wanted to create this sound, and they did it by crushing these notes together. So they created, instead of one or the other, that sound is very distinctive of pianistic blues, is really an effort to get at a note that is missing from our sophisticated Western scale that is missing a basic ingredient. And created in its own way a very rich and complex and interesting musical genre, which is unique to this situation. It wouldn't have been the same if the keyboard had the right note. This just shows you that what I said before, the note should be around 5/4. So if you play a trumpet, which is why trumpets are so good in jazz, you get this note right. It just comes out naturally as a harmonic. You play the guitar, you bend the note. So if you've ever done blues guitar, you'll notice that you play that E and you just bend it. You push the string up a little, and you'll hear that move. It's very distinctive blues guitar, which gets the right note. On the piano, you can't get it by that technique, so this crushing emerged. And let me give you a couple of examples of this. So this is one, this is in the key of G, and you'll notice if you can read music, there is that crushed note at the beginning of the piece. So that is the crushed crushing sound, which is also, popular music has embraced. So it really comes from the blues. It's interesting to go back a little further, back to the turn of the century, the last century, not the one we're in, the one before, and look at what happened in actually Kansas City, Missouri, where Scott Joplin was black performer, very talented, who wanted to bring, and he was more widely accepted by the establishment. He wasn't playing in the bars and the bluesy salons, he was playing in the salons and things of that kind. And so he wanted to introduce these ideas, but less grossly, and so he did it, and that's what basically a part of ragtime. Ragtime, of course, refers to the time and the time signature, but actually the characteristic of ragtime is exactly the same effect, but instead of playing these notes together and crushing them, they're played one after the other in a sequence. So I'll just show you that. This is one of his rags. This, by the way, is a diminished chord, if you're interested. The key here is this. So instead of the crushing, you've got the. So it's the same idea of getting at something that wasn't on the scale with these, what we call chromatic notes, but it really is driven, I think, by the same desire. Again, I don't believe this desire was a conscious, written down theoretical paper written in Nature by some physicist who said, you guys should try this. But that is an explanation for why this, I think, emerged. So one of the interesting, I want to stop in time with questions, but one of the interesting things that I've kind of realized is, mathematics and physics are related but different. Mathematics is the language which physics uses to study the world, right? So when you look at music, actually, I think you can see characteristics of both mathematics and physics, and this is what I'm trying to say here. And I describe it as ambiguities and axioms. Mathematics is axiomatic. In other words, you start with an assumption that if this is true, what can I do with that? Physics takes mathematics and tries to find how it fits to the world outside and says, does this actually fit the world? So physics is, in a sense, a real-world thing where often you realize it's not that simple, or, for example, I describe harmonics and strings as being integer multiples. Well, actually, because the string is not infinitely thin, that's not quite true. And the very high notes are flatter than they would otherwise be for a thin string, and physicists can explain this. Something to do with the way you wire piano notes is related to this. That means that piano tuners actually sharpen the bass notes so they'll overlap with the high notes when the harmonics overlap, because they aren't exactly linear. So a lot of the world is non-linear. But I think what I wanted to emphasize here was mathematics, because it's axiomatic, I think has a lot in common with the way composers work with this palette I described. The palette is, I think, not necessarily written down, but shared between us in a way that we sort of understand if we listen to music. I think we understand what that palette is, and that's the way in which we interpret music. We listen to Bach, we understand how he's taken those limited rules of counterpoint and made amazingly beautiful things with that we couldn't have done. But because we know those rules, we appreciate the creativity of what he's done. So I think, and musicians will tend to seek new axioms. So the break away from the scale, for example, to then introduce complexity, what happened 300 years ago, I think, was a desire to have new axioms. The first time people hear it, they rebel, they don't understand it. With time, they absorb it, and they learn the axioms, I think, and they then enjoy the creativity upon that. We're always looking for new, as creative people, new kinds of palettes on which to compose. So in that sense, I think music has something in common also with physics, because that's what determines the actual sounds that you hear, but also with mathematics through this axiomatic and ambiguity aspect, that it's the ambiguities, I think, that allow for an incredible creativity. I mentioned that Bach, for example, if you look at his pieces for the well-tempered clavier, the first set of pieces written for a well-tempered tuning, you'll notice that he doesn't explicitly go between keys. There's one in C and one in C sharp, one in D. But in each one, he hints at and jumps into other possible places in a very ambiguous way, which creates one of the tools he can use to create pleasure, the beauty of music. Now, there's a great deal of commonness. I'm not going to go into this in detail, but there's a great deal of commonness between music and physics and engineering that can be used, I think, to talk about these things. For example, harmonic analysis is nothing other than what X-ray diffraction does when it looks at crystal. It basically looks at spatial harmonics. And when we solved, for example, the Nobel Prize went 3 years ago to the structure of the ribosome, the critical machine in the cell, that was done by a form of harmonic analysis. If you're an engineer and you know about heat flow or designing bridges, you know how important harmonic or Fourier analysis is to understand. So I think you can use this to talk about some of these things. And you can also understand things like bandgaps and semiconductors and the nanotechnology. For example, these different colored particles are different in size. And when they're small enough, that you can't see the particles in looking at the solution, but there's billions of tiny particles in here. These particles are smaller than these, as a result of which they're blue and not red. And that has to do just exactly with the pitch of organ pipes, depending on the length of an organ pipe. In this case, it's the pitch of electrons inside these crystals, depending on the size of the crystal. And the pitch reveals itself as color. So there's a lot of interesting things you can develop, I think, from an educational point of view about using music as an example. The last one I will stop with is if I can get it to work, is to demonstrate what is called the wave-particle duality in physics. So this is the key to quantum mechanics, basically. This is the fact that, and it's really a property, partly a property of Fourier harmonic analysis, that we now know in quantum mechanics that everything has a so-called wave function, is a wave. But whether it really reveals itself as a wave or as a particle depends on its properties. And it's very simple to understand. This is one example of a wave packet, as it's called, where you can see many oscillations of the wave. And it's big enough that it's got a fairly well-defined wave character, but its position is kind of broadened by this thing. So its position is not very certain, but its wavelength is better, its frequency is better known. This is the reverse. It just has one oscillation. It's more localized. It's more like a particle, but its wave nature is suppressed. Well, that's all fancy jargon, but let's demonstrate with music. We can make a musical particle by simply changing the length of the note. I can create that note and that note on the synthesizer by changing the decay time of the note. So that's my last demonstration. I'm going to go to a pure sine wave here. That is just your unharmonic, raw frequency. So this would be kind of a boring, bit like an organ. But you can play notes with it, so it's so loud. It needs to be loud for the next bit. So let me take a simple thing like Twinkle, Twinkle, Little Star. And let me now change the duration of the notes and shorten them. So here's something in the middle. You can still sort of hear. Can you hear it in the back at all? It sounds like a percussive sound. If I now go to a even shorter note, which is going to be a little like this picture here, where there's less than one oscillation in it. Now remember, the note C has, let's take A, 440 hertz. Every 1/440th second is an oscillation. So if I get the note short down to about 1/200th of a second, I've only got 2 oscillations. And this is what it sounds like. Shorter. There it is. Well, you heard something there. It sounds like basically it's just going to sound like this. If I go to the extreme. It's like a percussive sound. So it's a particle. It's a musical particle. You cannot detect the pitch. You can't tell me if that was G or D or C, because you don't have enough information because it's too short. If on the other hand I extend it, then you can hear very clearly the wave nature, but it now takes some time. It's no longer localized in time. So really this is kind of, I think, a nice way to demonstrate, sorry to work perfectly, to demonstrate one of the very fundamental aspects of physics using music as an example. So I'm going to stop. This is just a summary of what I talked about. If you're interested, I've got some references here. I'll leave them up, and I'll probably put something on the web where you can get a copy of this. But my main point was to emphasize the very fundamental connection between mathematics and physics and creativity and music in a very interesting way. So hopefully it's provoked you, and I'm willing to answer any questions you have. Thank you.
Thank you.